Hello, this lecture will cover pages 245 through 250 of my lecture notes, so please print those pages out and have them in front of you as I present this final lecture of Chapter 7 on shift register counters. We're going to start out on page 245, and we're going to talk about two different types of shift register counters: the ring counter and the Johnson counter. First of all, ring counters do not count in a binary sequence. They don't count sequentially. Instead, they use words. Could be a 4-bit word, an 8-bit word, a 16-bit word that have a single bit high. Now, sometimes you can have more than one bit high, but remember, when you start with ring counters, generally speaking, you have to preset at least one of the bits high in order to circulate that one. These counters are primarily used to control a sequence of events or generate timing signals for sequential circuits. Let's take a look at a 4-bit ring counter here. I want you to notice we're using D flip-flops, and notice that the output, the Q output of one flip-flop feeds the D input of another. So if we go ahead and before we start this particular ring counter, let's say we're going to set Q3 to 1. So we would preset Q3 to a 1, and we would clear flip-flops 2, 1, and 0. So what you'd end up with is a 1, 0, 0, 0 starting out in our state diagram. That's how they're getting a 1, 0, 0, 1. Now this 1 could be anywhere. It just depends on your clear preset circuitry. You could start out in this state if you wanted to, a 0, 1, 0, 0 by clearing this flip-flop, presetting this one, and clearing this one, and clearing this one. Very easy circuitry to do that. We've done it in previous decoding circuits. If you take a look, we're going to assume we preset Q3 to a 1 and the rest are cleared. And notice that on the succeeding pulse, Q3 transfers to Q1, and the 1 transfers to here. Then the 1 transfers to here. Then the 1 transfers back to here. Then it goes to here. So basically what you do is you generate timing signals. Look at the master clock here. This is the master clock coming into the 4-bit ring counter. And the output of the least significant bit, like I said, feeds around to the input of the most significant bit. And notice this is a positive clock edge. So at every positive clock edge, this timing signal will move T3, T2, T1, T0, T3, T2, T1, T0. So what we've done here with this 4-bit ring counter is we've taken a master clock and we divided it down into 4 additional clocks. Now the clocks do not have the same duty cycle as these clocks up here. Notice they don't have the same period or the same frequency as the master clock, but nevertheless these are phases. These are different phases of the master clock timing. They're individual clocks of their own to be used in the circuit. If you take a look here, notice that the timing diagram is pretty simple. The timing diagram is fairly easy to see, but the state diagram is easier. It basically goes from a 8 to a 4 to a 2 to a 1. 8, 4, 2, 1 as you move this bit around. Notice if you cleared this, if you started out by starting a 0, 0, 0, 0, you'd end up with all zeros. There'd be nothing, there would be no ring action to this. You wouldn't be able to see it anyhow because there's no 1 being passed around. That's a ring counter. And we're going to look at some application of a ring counters. Let's take a look at, here's something I just drew for you to look at. I mean, real basic. Let's say you had to throw together some timing for a washing machine controller. So we're going to use, let's say, 18 D flip-flops, and we're going to tie them together like the previous circuit with the least significant bit wrapped around to the most one. And here's the outputs. This is Q1, Q2, Q3, Q4. I don't care if you started at this end and moved across. It depends how you lay out your flip-flops, but when you bring it out, the logic, here's your T1. So let's say you run a clock here. Let's put a clock in. Positive edge triggered clock. Real slow frequency, obviously. This is a washing machine, so you'd want to do it at a real slow frequency for a master clock. But at T1, T2, and T3, T1 and T2, you OR it together, that's when you open the water valve. How about T3? When you hit T3, that's when you open, you go through a buffer here, just to isolate the output circuitry here, or the output mechanics. You open the soap dispenser, open the soap valve. Then during T4, T5, and T6 and T7, depends on how much time you want, you OR, you wash. During T8, T9, and T10, any one of these high, as a timing phase, you rinse. You get the idea of how you can use a ring counter for any sequential control that you'd want to do. Simple sequential control. Let's take a look at page 246. Continuing on. Below is an example of a 6-bit ring counter controlling a sequence of operations or events. Notice how it can be used to generate, in this case, 6 phases, A, B, C, D, E, F of a master clock. Well, here you have a 6-bit ring counter. It's going to take 6 D flip-flops, or in a minute I'll show you how to use JK flip-flops, do the same thing. Here's your clock. You'd have to go ahead and you'd have to set one of these, preset one of these to a 1 with your initial reset circuitry. So you push a reset button, and it would take all but one of the flip-flops low by taking it to the asynchronous clear, and the one you wanted to preset, you'd take it to the preset input. That's all. And you'd get a 1. In this case, we got a 1 here at output A. Then the clock comes along, and A to B to C to D. And then it rings around A, B, C, and D. These are phases of the master clock. A, B, C, D, E, F. A, B, C, D, E, F. I didn't put the E and the F down here, but I said etc., etc. You get an idea. It's going to move A, B, C, D, E, F. You know what? This timing isn't exactly right. When I did this, this should be a E and F down here. This A signal should not happen until out here somewhere. So look that over, make sure you understand it. As a 6-bit ring counter, I did it as a 4-bit ring counter, A, B, C, D. But how can we use a 6-bit ring counter? Well, in an application I have that we talked about before, in this microprocessor controller, this is on page 148, matter of fact. We looked at it again. It's that microprocessor architecture. Below is another example of a ring counter used to generate timing signals. We're going to draw a timing diagram for the 6-bit ring counter. This is your 6-bit ring counter up here. And it's going to generate timing signals for this control matrix down here. Remember we talked about the micro word that enables things onto the bus and loads things onto the bus? Well, here's that micro word. If you take a look at lecture notes, page 148, you'll see that micro word coming out of the controller sequence down here. It's right here. It's this micro word coming out of the controller sequencer. And that makes the data dance on that tri-state data bus. But it's dependent upon a couple things. It's dependent upon what type of instruction we're doing coming from the instruction decoder circuit, and what timing phase you're in up here. These are the different timing phases: T1, T2, T3, T4, T5, and T6. Notice what we're doing is we're using JK flip-flops. And basically, to use a JK flip-flop, show you this real quick. To use a JK flip-flop, all you have to do, we'll do it from left to right here. This is your J1, this is your K1, this is your J2, and this is your K2. This is your output, Q and bar. This is your output, Q and bar. Here's your inputs. So there's 2 JK flip-flops. Well, what you have to do, let's put this in. This is your Q1. This is your Q1 bar. Here's your Q2. And here's your Q2 bar. You just feed the Q outputs to the J, and you feed the Q bar outputs to the K. You continue with that. This goes to J3, this goes to K3. There's a 3-bit ring counter. If we take this out to here, There you go. Take the output here and bring it around to the most significant bit, and take this K here and bring it around here. There, I'll do that if you will. There's your 3-bit ring counter. Where's your outputs taken from? There's your one output for Q1. And here's your output for Q2. And here's your output here. Let's do this. There's your Q3. There's your 3 outputs, the 3-bit ring counter, using JK flip-flops. Well, that's all they did here. To get timing sequences. Notice that for your they're going to send us, it's difficult to see on your paper, but this is a low active clear right here. When this goes low, notice you're clearing every one of these JK flip-flops. And if you want to look at the pinouts, that's why I have this on the next page. The pinouts for these JK flip-flops here is right here. So you should take a look. And why did the engineer, for instance, take pin 10 and 13 and 10 and 13 and 10 and 13? Well, there's 2 JK flip-flops in here. There's 2 JK flip-flops. So you're going to need 1, 2, 3. You're going to need 3 of these LS107 devices to build this ring counter right here. Notice the Q bar is gone to the J on the first one. Well, why would they do that on the first one? Because they're taking the Q bar output. They don't have to use the preset to set a 1. Because T1, anytime you have a clear pulse right here, anytime this is cleared, this flip-flop is cleared, that Q bar output's going to be a 1. So you're going to start out with T1. A low active clear here, we'll put a T1 at 1, and all these will be low, 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 because they're all coming off the Q output. You're looking at this from left to right. Here's T1, here's T2, here's T3, here's T4, here's T5, and here's T6. What you're going to notice when a low active clear happens here, you're going to clear every one of these. But when you clear this one, the Q goes to a 0. This is flipped around here. And the Q bar goes to a 1. So you start with a 1 here. And then that 1 is passed to here, and it's 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 brought around, and it's passed to here. So that's how you get your timing. Your timing is T1, T2, T3, which is your fetch cycle for this microprocessor. It's a time needed to fetch the instruction from memory, making this data dance down here. And we're not going to get into the specifics, but T1, T2, T3 is a fetch cycle. T4, T5, T6 is the execution cycle in this very simple processor. And in your microprocessor chips, you're going to get to that course later, you'll have different timing phases. You'll start out with a fetch, and then you'll have execution. Then you'll have fetch, and you'll have execution. In this simple model here, T1, T2, T3 is your fetch cycle. You're getting the instruction from memory, and you're putting it into the memory register. And T4, T5, and T6 is when it executes, generating microcode. And if I can show you that here, let me point that out just so you have a clear understanding of what I'm talking about. Here on page 147, I said 148 before, but it's 147 obviously. If you take a look here, you know, during T1, T2, and T3, that ring counter is inside this controller sequencer. That circuitry I just showed you is inside here. So during T1, T2, and T3, what you're doing is you're fetching what's in memory and you're bringing it into the instruction register. And during T4, T5, and T6, you're executing that instruction by generating this microcode here to move the data around this processor. You're executing. So with that, I would like you to do the timing diagram right here. I'd like you to assume to start out with that the clear in this circuitry right here, assume the clear is low. And there it is. Put this clock in. In other words, do this much of it. I want you to go ahead and draw that much of the timing in, and then I want you to do the remaining for. I want you to see if you can do the rest of this for T1, T2, T3, T4, T5, and T6. based on looking at this pinout, but mostly just taking some time and looking at the actual circuitry. Looking at this actual circuitry right here. And here's your answer. Obviously, there's your answer. That's what you should end up with. That's ring counters. I showed you how to generate a ring counter using a D flip-flops and using JKs. And then finally, we want to move to Johnson counters. A Johnson counter. I want you to read just very briefly about the Johnson counter there. The basic ring counter can be modified slightly to produce another type of shift register counter, which will have a somewhat different properties. In this case, the Johnson counter, which is also called the twisted ring counter, is constructed exactly like a normal ring counter, except that the inverted output of the last flip-flop is connected to the input of the first flip-flop. So if we look here, I'm showing you a 3-bit Johnson counter here. Notice that we don't take the LSB and bring it around the Q output. We don't bring it around to the most significant input. We take the Q bar output and we bring it around. That's why it's called a twisted ring counter or a Johnson counter. And it gives us some unique properties. Notice in this case right here, we can clear everything. We can clear the Johnson counter because we're taking a Q bar output here, which will be a 1. So if you take a look from the cleared state, it's going to count, in this case, 4, 6, 7, 3, 1, 0. 4, 6, 7, 3, 1, 0. And you could see it on the clock pulses here. The mod number of the Johnson counter is always equal to twice the number of flip-flops. Wow. Think about that. That's just a rule of thumb engineers know. And it's useful in application, but you don't have time to get into a lot of application. This is a 3-bit Johnson counter. So it's going to be, if you connect it up like this, a 3-bit Johnson counter is a mod 6 counter. 1, 2, 3, 4, 5, 6. There it is. So if you build a 4-bit Johnson counter, a 4-bit Johnson counter is going to be a mod 8 counter. The last thing I want to leave you with is what they mention in the book here. Johnson counters represent a middle ground between ring counters and binary counters. A Johnson counter requires fewer flip-flops than a ring counter, but generally more than a binary counter. It has more decoding circuitry than a ring counter, but is less than a binary counter. Thus, engineers sometimes use it as a logical choice in certain applications. And that concludes the lecture.